The graph that you see here is the result of an experiment that I did. I took some air, which is a gas. I trapped it in an Erlenmeyer flask, which is made of glass, and so its volume can't change. And because I trapped it with a good rubber stopper, I assumed that the number of particles can't change. So that's a good situation for us to measure or determine what's the relationship between pressure and temperature of the gas. I put a tube through the stopper, and this tube was attached to a pressure sensor, and so that's how I could measure the pressure. I also had a temperature probe that allowed me to measure the temperature, but I couldn't put that right inside the air that was in the flask. So what I did was I put it immediately outside of the flask. I heated up some water in a large beaker that was big enough to put the whole flask inside, and got it up to around boiling or so, and then I started to let it cool off with the flask inserted inside the water bath. I put the temperature probe in the water bath, and so the air inside the flask was approximately the same as the temperature outside of the flask in the water as it cooled down. And about every 10 degrees or so, I used my data logging software to measure the temperature and the pressure, and that gave me a point on this graph. So as it cooled down, I got several points, and I have to say that I think I was not stirring the water bath at the end and when we got into the 30s, because I have 3 points here that I'm suspicious of. I feel like something weird was going on, and I think I'm going to take those out of my data set. I think I'll do that right now. I'll just strike through those data cells. And get them off of the graph because I don't think they're valid. Then the other thing I did was I took the flask out of the hot water bath, and then I inserted it in a slush water bath, which was around the freezing point of water. And then I removed the ice so that the cold water could begin to warm. And as it warmed, I collected some more data, and you see that down here at the bottom of the range. It looks like it's possible that a straight line relationship might be a good model for how pressure responds to temperature. I'll check the fit by doing linear regression. And in fact, it's reasonable to conclude that a line's a pretty good fit. I get a correlation of 0.9943. And so what that means is that I could say that pressure equals a constant number, that's the slope, in this case 2.104 millimeters of mercury for every degree C, times the temperature plus a vertical intercept, which is 577.9 millimeters of mercury. So what that really means is when the temperature is zero, 577.9 millimeters of mercury is what the pressure is. There are two reasons that this is a little bit problematic for scientists. One is when the temperature is zero, that doesn't really mean it's zero, like the coldest possible temperature there could be. It's just an arbitrary value that Anders Celsius set as the 0 point, is the freezing point of water. And temperatures, in fact, we know can go down below that. And so that means that there's a vertical intercept. And the vertical intercept is a problem too. If you studied the number of particles and pressure and how they relate, you get this simple ratio that says pressure divided by number of particles is a number that never changes. And that's easy to interpret that effect then. Whatever happens to the number of particles, the same thing also has to happen to the pressure. So it would be nice to be able to say, in this case, that pressure divided by temperature is a constant. But using this Celsius scale, that is not true. So what we want to do is find a way around this. And so scientists, in the effort to do that, figured out that if you traced this back, if you extrapolated this line, in other words, and figured out where would this line cross the zero for pressure, that would have to be the coldest temperature you could possibly be. And this is based on the theory of particles as a model of matter. If the particles moving and colliding with the pressure gauge is what causes pressure, when they stop moving, then there's no pressure. And when they stop moving, by the definition of what temperature is, that's when your temperature is really zero. That's the coldest it can possibly be. And a whole new temperature scale was developed when that was done. So let's try that. I want to put that line back on there. I'm going to change the scale. I'm going to go to our axes here, and I'm going to change them so that I can see this line actually cross 0 by sliding the scale. Not down to 0 yet. I have a long ways to go on the vertical axis. There we go. I'm just going to keep sliding and look for where does this line cross 0. There it is, right there, where I have my cursor placed right now. That is theoretically the coldest possible temperature that you could ever have. And the reason for that is because the pressure would have at that point dropped to 0. Now this is really theoretical because we didn't actually get any points that cold, but if the pattern follows, and it looks like it would, we would have a temperature of negative 273.9, it looks like, when the pressure dropped to 0. So that's the coldest possible temperature there could be. And that's actually in pretty close agreement to what scientists have found by doing experiments like this over the ages, and from a lot of different directions. A lot of different experiments, some of them which don't have anything to do with gas, lead us to the same conclusion. So the standard value is actually 273.15. 273 is close enough for our purposes. So there's a new temperature scale that starts there, and it's called the Kelvin scale. So 0 Kelvin, let me start this over again. 0 kelvins is the same as negative 273 degrees Celsius. So you can change temperature scales from Celsius to Kelvin by just adding 273 to any Celsius temperature. So I take a Celsius temperature plus 273, and that equals my Kelvin temperature. Now, as long as I use a Kelvin temperature scale, I can, in fact, use this simple relationship that says pressure divided by temperature is a constant number. And that allows us to use a simple proportion that says, if temperature doubles, pressure has to double. If temperature cuts in half, pressure also has to cut in half, like we did for other relationships.